Today, let us start learning a new session. Okay, in the previous section, we were talking about the conductor in an electric field. So in this section, we will move forward to talking about an insulator in the electric field, to talking about the influence of the dielectrics on the electric field. First, let us talking about an experiment. Consider I have two planes, one plane with charge positive Q and another plane with negative Q. And then we know that there should be a constant electric field in between of them. If I use the equipment to measure the electric field in between of them, saying I can measure the voltage between those two planes, and then we will have a voltage rate measurement. And then this is for the vacuum situation. Then if I fill in some materials in between the two planes, saying any kind of material, then we will find that the voltages will be decreased. That means such kind of material will be reduced the electric field. This is we called relative dielectric constant. And from the measurement, we always found that such kind of constant will be always larger or equal to 1. That means any kind of materials will be reduce the original electric field intensity. And then we can do the measurement of several different materials, and you will find that the relative dielectric constant will range from 1 to very large. That means different materials will reduce the electric field in different way. And then the next question we want to answer is like this: why the materials will reduce the electric field? We know that all materials will be composed of the atoms of molecules, and from the charge properties of the molecules, we can divide the materials into two parts. First, let us talk about the non-polar molecules. What is non-polar molecules? Non-polar molecules means the density distribution of positive charge and negative charge will be overlapped totally. That means we will do not have the net electric dipoles. However, for another molecules called polar molecules, you will find that the density distribution of the positive and negative charge is not totally overlapped, which means we have the finite electric dipole moment. And then, if we put those two kinds of materials inside the electric field, you will find that when there is non-electric field present, the non-polar molecules, there should be no net electric dipole moments. And for the polar molecules, even though for each molecule you will have a net electric dipole moment, however, because your dipole moment with all the direction pointing with equal possibility, then all the dipole moment will be cancel each other. And then if there is no electric field, even in the polar molecules, there is also no net dipole moment. And then let us talking about there is a electric field in. If we're talking about non-polar molecules, that means under the electric field, the positive and the negative charge will be applied to the electric force, and then this force will drive away those two particles, and such kind of displacement will be caused the finite dipole electron moment, and we call this displacement polarization. And then you will find that the net effect of such procedure will accumulate charges on the surface of the materials, and there should be a bound charge on the two outer edges of the system. And if we're talking about the polymoleculars, because it is a dipole moment associated with each molecule, and under the electric force there is a finite angular momentum, and the polymoleculars will be rotate in the field. And it will be rotate along the direction of the external field. This is called rotational polarization. And it has also the same result regarding the bound charges of the system on top of the surface of the system. Then, from those two kind of polarization procedure, you will find that there should be a bound charge on the surface of the material. And if you zoom in on such kind of bound charges, you will find that the electric field caused by these bound charges will be in the opposite direction of the external original field. That means the bound charge will be reduced to the original E0, then at the equilibrium system you will get the final electric field, which will be the superposition of E0 and E prime, and the E prime and E0 has the opposite direction. Then in that sense, we can explain why the materials will reduce the original electric field. Then we can define a quantity to describe how large the polarization is. We can define the electric polarization, call it P. P has the definitions like this. P is the net electric dipole moment of the molecules per unit volume of the dielectric. And in the isotropic materials, we have the relations like this. P is proportional to the E, and the constant is E squared times equals to R minus 1. Equals to R is the relative dielectric constant. Then let us build on the relation between the sigma prime, the bound charge density, and the polarization. We can choose a cylinder geometry which has the ds as the bottom and the top area, and L is the length. And then we can calculate the total charge inside this volume and call it dq prime. dq prime is equals to q times n0 L times ds cosine theta. Nl is the density of the charged particles. And then we will get that dq prime equals to p dot ds. And then we can divide the ds into the left hand of the equation. We will get that sigma prime equals to p dot n. Then we will build the distribution of the bound charge and p polarization. By using such kind of relation, we can calculate the bound surface charges. Consider such kind of system with two charged planes. If we input the dielectric materials inside the two planes, and we can calculate the bound charges, one called minus sigma prime, another called positive sigma prime. Then from the Gaussian law, we can get that the original electric field intensity will be equals to E0 equals to sigma 0 divided by epsilon 0. And then we also know that the bound charge will be equal to E prime equals to the sigma prime divided by epsilon 0. And then the total electrical intensity will be the superposition of E0 and E prime. And by substitution in the relation of the above, we can get the final result. And then we can just rewrite the result as here. Then we got that the bound charge, the sigma prime, will be equals to 1 minus 1 divided equals to R times equals to 0. We can also use the P relation between P and sigma to define and to find the result of the bound charge. And we can derive P from the relation between P and E, we can find that P is equal to the e to 0 times e to r minus 1 times E. And then we use sigma pi equals to P dot n, we can get that sigma pi equals to the e to 0 times e to r minus 1 times E. See you guys next time.